Before the first star ever burned, before the universe learned how to shine, there was already something happening. Not light, not heat, not even the familiar sense of time passing. There was expansion without illumination, motion without glow. A universe filled with energy, particles, and structure, yet almost entirely dark. This is not speculation. It is one of the most carefully measured chapters in modern cosmology. A long, silent era after the Big Bang, when the universe was real, vast and active, but still invisible. No stars, no galaxies, no eyes that could ever see it. If this quiet journey brings you even a moment of peace, I'm deeply grateful you're here. A gentle like or a soft tap on subscribe helps keep these calm explorations alive, and I hold that support with sincere thanks. Now, let's begin with the first truth. Part 1. What existed before light could exist at all? If you could travel backward through cosmic history, past galaxies, past stars, past even the first atoms, you would not arrive at nothing. You would arrive at a universe already full, already expanding, already governed by physical laws. In the earliest moments after the Big Bang, energy filled every point in space. Particles collided constantly, and yet there was no light in the way we understand it. The universe was not empty. It was simply opaque, too dense and too hot for light to move freely. To understand this, it helps to release the idea that light is required for existence. Light is not the beginning of reality. It is a messenger, a consequence, something that emerges only when conditions allow it to travel. In the earliest universe, those conditions did not yet exist. Space itself was smaller, denser, and hotter than anything we can easily imagine. Every region was packed with energy and matter so tightly coupled that photons, the particles of light, could not escape their surroundings. At this stage, the universe was less than a second old. Temperatures exceeded trillions of degrees. Quarks and gluons moved freely in a dense plasma, constantly interacting. As space expanded and cooled, these quarks combined into protons and neutrons. This happened quickly, within minutes, but even then, light still could not travel. Free electrons filled space, and wherever a photon tried to move forward, it was immediately scattered. You can imagine this early universe not as darkness, but as a blinding fog. Not the quiet darkness of night, but a thick glowing haze where visibility is impossible. Light existed everywhere, yet nowhere could it go. Photons bounced endlessly, absorbed and re-emitted by charged particles. There was no clear path, no open distance. The universe was bright, but it could not be seen. This distinction matters. Darkness in cosmology does not always mean absence of light. Sometimes it means confinement. The laws of electromagnetism tell us that charged particles interact strongly with photons. In a plasma-filled universe, free, electrons act like countless mirrors and obstacles. Each collision redirects light, trapping it in place. Until electrons are bound into neutral atoms, light cannot travel far. As you rest and breathe, it's worth pausing on how unfamiliar this is to everyday experience. On Earth, light moves almost effortlessly through air. Even clouds allow partial visibility. But the early universe was denser than any fog, thicker than any cloud, more crowded than any material state we encounter. Space itself was filled with particles at nearly uniform density, leaving no room for transparency. And yet, despite this chaos, the universe was remarkably smooth. Measurements of the cosmic microwave background show that the early universe was uniform to 1 part in 100,000. That means that even in its turbulence, it was balanced. No stars yet, no galaxies, just a nearly even sea of energy, expanding calmly under the influence of gravity and the initial conditions set by the Big Bang. Time still flowed during this era. Expansion still occurred. The universe aged second by second, even without visible markers. Physical processes provided the clock. As temperatures dropped, new kinds of particles became stable. As densities fell, interactions slowed. Time was written not in light, but in transformation. One of the most important transitions was the formation of atomic nuclei, a process called Big Bang nucleosynthesis. Within the first few minutes, protons and neutrons fused into the nuclei of hydrogen, helium, and traces of lithium. This set the elemental foundation of everything that would come later. Every star, planet, and living thing would eventually be built from this simple recipe, established in darkness. Still, even after nuclei formed, electrons remained free. The universe stayed ionized, light remained trapped. For hundreds of thousands of years, this condition persisted. Space expanded steadily, cooling gradually, like an ember slowly losing heat. There was no sudden change, no flash, just patience. If you could stand within this early universe, which you cannot, but if you could, there would be no direction to look, no horizon to orient yourself. The universe was the same everywhere. No stars punctured the fog, no shadows existed. There was no contrast, no night sky, no points of reference, just a uniform glow pressed in from all sides. This is one of the quiet truths of cosmology. The universe did not begin as a dramatic spectacle. It began as a process. Order emerged slowly, guided by simple laws repeated across unimaginable scales. Gravity pulled gently, expansion stretched space, particles interacted, cooled, combined. Light, in this sense, was late to the story. It required separation, it required distance, it required calm. Only when electrons finally bonded with nuclei to form neutral atoms could photons travel without constant interruption. That moment, still far ahead in this journey, would release the oldest light we can observe today. But here, in this first chapter, before that release, the universe existed without illumination as we know it. It was real, structured, and evolving. It simply had no windows. There is something quietly grounding about this idea. The universe did not rush toward visibility. It did not hurry to be seen. For hundreds of thousands of years, it existed entirely without observers, without images, without stories. And yet, every second of that time mattered. Every interaction shaped the future. As you lie still now, it may help to imagine that kind of existence, a reality without brightness or darkness, without edges or features, just presence, just slow change, a reminder that meaning does not depend on spectacle. In modern physics, we often say that the universe began hot and dense, but those words are placeholders for something deeper. They describe a state where energy dominated, where distance was compressed, where light had no freedom. It was not emptiness, it was fullness taken to its limit. And as expansion continued, that fullness gradually loosened its grip. Space grew, density fell, interactions softened. The universe was quietly preparing for transparency, for structure, for the first long journeys of light. But that comes later. For now, it is enough to know that before the first star ever burned, before the first glow crossed open space, the universe was already alive with motion, already obeying laws, already carrying within it everything that would one day shine. And as we continue this quiet journey, one question naturally follows. If light existed but could not travel, what finally allowed the universe to let it go? Part 2. Why the early universe was bright yet completely dark. It sounds like a contradiction, but the early universe glowed with energy while remaining invisible. Photons existed, but they were trapped, endlessly scattering off charged particles like electrons and protons. Light could not travel in straight lines. Instead, it bounced, absorbed, and re-emitted so frequently that the universe behaved more like a thick fog than open space. Illumination existed, but visibility did not. To understand how something can be bright and dark at the same time, it helps to think of light not as a simple glow, but as motion. Light is information carried by photons, and information only becomes useful when it can travel. In the early universe, photons were everywhere, but they were not free. Every attempt to move forward was interrupted almost instantly by an interaction with matter. At this stage in cosmic history, the universe was filled with plasma. Not plasma as we imagine in science fiction, but a real physical state where electrons are not bound to atomic nuclei. Protons and electrons moved independently, constantly colliding, constantly interacting. This made space itself opaque. Any photon trying to move was scattered by free electrons through a process known as Thomson scattering. The path of light was not a straight line, but a random walk. Imagine standing inside a dense storm cloud. Lightning may flash around you, illuminating everything for a moment, but you cannot see far. Light reflects, refracts, and scatters so completely that distance disappears. The early universe was like that, except far denser, far hotter, and extending in every direction without edge. In this environment, brightness had no structure. There were no points of light, no gradients, no shadows. Every location was flooded with roughly the same energy. The universe did not have contrast yet, and without contrast, visibility has no meaning. Seeing requires difference. It requires light to originate somewhere and travel elsewhere. In the early universe, everything was everywhere. This is why cosmologists say the universe was in thermal equilibrium. Energy was evenly distributed. Temperatures were nearly identical from place to place. Photons carried energy, but they did not carry images. They did not reveal shapes or distances. They simply exchanged momentum and heat with matter over and over again. As you listen now, it may feel strange to imagine a universe without direction or depth. We rely on vision to orient ourselves, to understand where we are. But in this early epoch, orientation was impossible. There was no up or down, no near or far in any practical sense. Space existed, but it did not yet allow perspective. Time, however, continued to move forward. Expansion slowly reduced density. Temperatures dropped steadily. With each passing second, the universe became slightly less hostile to traveling light. But the change was gradual, unfolding over hundreds of thousands of years. During this long interval, something important was happening beneath the fog. Tiny differences in density, seeded in the earliest moments of cosmic inflation, were beginning to grow. Regions that were just slightly denser than average pulled in more matter through gravity. These differences were incredibly small, but they mattered. They were the first hints of structure. Yet, even these growing variations remained hidden. The fog concealed everything. Light could not yet trace the contours of matter. The universe was shaping itself in darkness, preparing the framework of galaxies long before they could be seen. This hidden activity is one of the most profound ideas in modern cosmology. The visible universe is not the whole story. Much of its structure was determined before light ever had the freedom to travel. What we see today is the illuminated outcome of processes that began in obscurity. As expansion continued, electrons gradually lost energy. Eventually, conditions reached a critical threshold. Protons and electrons could finally bind together to form neutral hydrogen atoms. This process is called recombination, though it was really the first combination. When electrons became bound, they stopped scattering photons so efficiently. Suddenly, the fog began to lift. Photons that had been trapped for hundreds of thousands of years were released. They streamed outward in all directions, carrying with them a snapshot of the universe at that moment. This light still exists today, stretched by cosmic expansion into microwaves. We call it the cosmic microwave background. But here, in this second part of the story, we are still before that release. We are still in the era where brightness does not equal visibility, where energy fills space, but space does not yet allow light to speak. It's worth reflecting on how counterintuitive this is. In everyday life, brightness and clarity go together. More light means better vision. But physics does not always follow intuition. In the early universe, there was too much light, too much interaction, too much density. Light was overwhelmed by its own abundance. There is a quiet lesson here. Clarity often comes not from addition, but from separation. Only when space expanded enough, only when particles stepped back from constant interaction, could light finally travel and reveal structure. As you rest, breathing slowly, imagine this ancient brightness without images. A universe glowing uniformly, softly, endlessly, without edges. No night sky, no dawn, just presence. This era reminds us that darkness is not always absence. Sometimes it is excess, too much connection, too much interaction. Only with distance does meaning emerge. When we look at the universe today, we are seeing the long aftermath of that transition. Light now travels freely across billions of light years, carrying stories of stars, galaxies, and planets. But for a long time, The universe existed without stories, without images, without witnesses. And still, it was not incomplete. The laws of physics did not wait for light to appear. Gravity worked, expansion continued, matter evolved. The universe did not need to be seen to become what it is. This is part of what makes cosmology so quietly humbling. Everything familiar, everything visible, rests on a foundation built in darkness. The earliest chapters of reality unfolded without illumination, yet they determined everything that followed. As we move forward in this journey, we will watch the fog thin, the darkness change character, and light finally gain the freedom to travel. But for now, we remain in this strange, glowing obscurity. A universe bright beyond measure, and yet completely unseen. And as the brightness slowly loosened its grip, one question began to matter more than any other. What had to change for light to finally move freely through space? Part 3. The fog made of plasma, not clouds. When we imagine darkness, we think of emptiness. But the silent era of the universe was dense beyond comprehension. Space was filled with plasma, a hot soup of free electrons and nuclei. This plasma scattered light efficiently, preventing any photon from traveling far. In this state, the universe was smooth and uniform, almost featureless, yet humming with activity at every scale. To understand this fog, it helps to let go of the images we usually carry with us. This was not a fog of droplets or dust. There were no clouds drifting through empty space. Instead, space itself was the medium. Every region was filled with charged particles moving at tremendous speeds, colliding, separating, and colliding again. The fog was not something inside the universe. It was the universe. Plasma is often called the fourth state of matter. On Earth, we encounter it in lightning auroras or inside neon signs. But in the early universe, plasma was not rare or fleeting. It was the dominant condition of reality. Temperatures were so high that atoms could not exist. Electrons were stripped away from nuclei, leaving a sea of charged particles that interacted intensely with light. In this environment, photons could not travel freely. Each photon carried energy, but as soon as it tried to move, it encountered an electron. The interaction redirected it, changed its direction, sometimes its energy. Over and over again, photons scattered. Their paths became tangled, like a traveler trying to cross a crowded room where every step leads into another collision. Because of this constant scattering, distance lost its meaning for light. Even though space itself was expanding, photons could not carry information across it. They were trapped locally, exchanging energy but not revealing structure. The universe was luminous, but blind. And yet, despite the chaos of constant interaction, the plasma-filled universe was remarkably calm on large scales. Gravity and expansion worked together to smooth out extremes. This is why cosmologists describe the early universe as homogeneous and isotropic. It looked the same in every direction, not because nothing was happening, but because everything was happening everywhere. As you rest now, you can imagine this balance: motion without turbulence, activity without noise. The universe was not quiet because it was empty. It was quiet because it was evenly full. This uniformity was not perfect. Tiny variations in density existed, differences so small they would be easy to miss. But these variations mattered. They were the seeds from which all later structure would grow. In the plasma fog, gravity was already at work, gently pulling denser regions together, even though nothing could yet be seen. The fog hid these early changes completely. There were no visible boundaries, no glowing knots, no dark voids. Everything was submerged in the same glowing medium. The universe had depth, but no contrast. It is important to understand that this fog did not block light in the way walls block light. It did not absorb it and make it vanish. Instead, it scattered it endlessly. Energy remained. Information did not. In physics, this distinction is crucial. The universe conserved energy carefully. Nothing was wasted. Photons continued to exist, exchanging momentum with matter. The fog was dynamic, alive with microscopic motion, even though macroscopic features were suppressed. During this era, the universe expanded continuously. As space stretched, the plasma cooled. Particle energies slowly decreased. Interactions became slightly less violent, slightly less frequent, but for a long time, nothing qualitative changed. The fog persisted. From the perspective of modern observers, this long period can feel uneventful. Hundreds of thousands of years passed without stars, without galaxies, without light traveling freely. But in cosmic terms, this was a necessary incubation. The universe was stabilizing, settling into conditions that would allow complexity later. You can think of this plasma fog as a kind of preparation, a time when the universe was learning restraint. When density thinned just enough, when temperature dropped just enough, something new could happen. But until that moment, the plasma ruled. Electrons, because of their small mass, played an outsized role. They scattered photons efficiently, acting like gatekeepers that prevented light from escaping. As long as electrons remained free, the universe stayed opaque. This simple fact shaped the entire early history of visibility. And yet, even in this opacity, information was being stored. The tiny density fluctuations were imprinted in the plasma itself. Sound waves rippled through it, oscillations driven by the push and pull between gravity and radiation pressure. These waves left subtle patterns that would later be frozen into the cosmic microwave background. These patterns are still visible today, measured with exquisite precision by satellites. They tell us that even in the fog, the universe had rhythm. A quiet, mathematical rhythm written in temperature differences and density waves. If you could somehow listen to the early universe, which again you cannot, but if you could, you would not hear silence. You would hear a steady hum, the sound of pressure waves moving through plasma, not sound in the way air carries sound, but oscillations of energy and matter coupled together. This is one of the most beautiful aspects of modern cosmology. The universe left behind a record of its fog. Long after the plasma cleared, its patterns remained. As the universe continued to cool, electrons slowed down, protons waited. Eventually, conditions favored a new arrangement. Electrons began to bind to nuclei, forming neutral atoms. This single change altered everything. Neutral atoms do not scatter light nearly as efficiently as free electrons. When electrons became bound, the fog thinned rapidly. Space transformed from opaque to transparent. Photons that had been trapped since the beginning were finally able to travel. But that moment lies just ahead in our story. Here, in this part, we remain in the plasma era, a universe without clouds, without emptiness, without visibility. A universe filled to the brim with matter and energy, so full that nothing could be seen through it. There is something deeply calming about this image. No sharp edges, no isolation. Everything connected, everything interacting, everything sharing the same space. In this state, the universe was not yet divided into objects. There were no stars to separate themselves from darkness, no galaxies to carve identity out of space. Individuality had not yet emerged. And yet, individuality was inevitable. The laws of physics ensured it. Gravity would amplify tiny differences. Expansion would stretch space. Cooling would allow new structures to form. The fog was temporary. Necessary, but temporary. As you lie still now, breathing evenly, you might imagine this ancient plasma as a reminder. That clarity does not come instantly. That form emerges slowly. That even the universe itself required patience before it could see. And as this fog gradually thinned, another question began to surface. If the universe was once completely opaque, how did it finally become transparent at all? Part 4. How time passed without stars to measure it. Without stars rising or setting, without planets orbiting suns, time had no familiar markers, yet physics tells us time still flowed. Expansion continued, temperatures dropped, particles evolved. In this era, time was measured not by light but by change itself, by how quickly the universe cooled and how energy transformed as space stretched. It is difficult to imagine time without clocks, even harder to imagine time without skies. For us, time is anchored to repetition, days, nights, seasons, heartbeats. We measure duration by cycles of light and shadow. But in the early universe, there were no cycles yet, no orbits, no rotations, no surfaces turning toward a star. And still, time moved forward. In physics, Time does not require observers or calendars. It requires only change. As long as the universe evolves from one state to another, time exists. In the silent era, that evolution was slow, steady, and global. The entire universe participated in the same process at once. The most important clock of this era was expansion itself. From the very beginning, space was stretching, not expanding into anything, but expanding as space. Distances between points increased everywhere, uniformly. As space expanded, energy spread out, temperatures dropped. This cooling was not random. It followed precise mathematical relationships described by cosmology. Early on, the universe cooled extremely fast. In the first second, temperatures dropped from unimaginable extremes to merely extraordinary ones. Later, cooling slowed. Minutes passed, then hours, then thousands of years. As expansion continued, each moment lasted longer than the one before. Time did not slow down, but change became more gradual. This is how physicists reconstruct the age of the universe. They do not count days or years. They follow temperature. They trace how hot the universe must have been at different stages to produce the particles and structures we observe today. Time is inferred from transformation. During the silent era, the universe moved through distinct physical thresholds. At certain temperatures, some particles could exist. Below those temperatures, they could not. When the universe cooled enough, quarks combined into protons and neutrons. Later, nuclei formed. Still later, electrons slowed enough to eventually bind to atoms. Each of these transitions marked time passing. You can think of it as a kind of cosmic aging. The universe began too hot to hold itself together. Then, step by step, it became calm enough for complexity. This was not guided by intention or direction. It was guided by physics responding to expansion. Without stars, there was no local sense of time. No region experienced night or day. Everything happened everywhere. The universe did not yet have places that evolved differently from others in visible ways. Time was universal in a sense we no longer experience. Later, gravity would break this uniformity. Galaxies would form, clocks would diverge. Time would flow differently near massive objects. But here, in the early universe, time was remarkably synchronized. The same cooling happened everywhere at once. This makes the silent era unique. It was one of the last times the universe shared a single, nearly global rhythm. As you lie still now, you might imagine that rhythm as a slow breath. Expansion, cooling, expansion, cooling, no ticking, no urgency, just progression. Physicists sometimes describe this era using the concept of the scale factor, a number that tells us how big the universe is relative to its size at another time. As the scale factor increases, the universe ages. In this language, time is not a line, it is a stretch. Another way scientists track time is through particle interactions. In a hotter universe, particles collide frequently and violently. As it cools, collisions become rarer and gentler. Reaction rates slow. Certain processes freeze out, meaning they stop happening because conditions no longer allow them. Each freeze-out marks a moment in cosmic time. For example, neutrinos decoupled from matter very early, streaming freely through space long before photons could. Their decoupling is a timestamp embedded in the universe. Even today, a background of relic neutrinos fills space, carrying information from a time when the universe was less than a second old. Photons, by contrast, remain trapped much longer. Their release would mark a later time, hundreds of thousands of years after the beginning. Different particles, different clocks. This layered timing shows us that the universe did not experience time as a single event, but as overlapping processes unfolding at different rates. Time was not empty. It was structured. And yet, for anything that might have existed then, which again we must say did not, time would have felt featureless. No landmarks, no milestones, just gradual change. This raises a subtle point. Meaningful time often requires memory, something to compare now to then. In the early universe, there were no stable structures to carry memory forward. Everything was fluid, interchangeable, constantly interacting. Only later, when atoms formed, when matter clumped, when objects persisted, could the universe begin to store its own history in visible ways. Until then, Time left no scars. It passed, but it did not leave marks that could be easily read. Modern cosmology allows us to reconstruct this era only because of what came after. The cosmic microwave background, the distribution of galaxies, the abundance of elements, all carry encoded information about how long the silent era lasted and how quickly it unfolded. Time, in this sense, is inferred backward. There is something quietly profound about that. The universe kept time long before anything could remember it. It aged long before anything could notice. As you breathe slowly, letting your body rest, consider that your sense of time is built on repetition and contrast. Seconds tick because something changes in a familiar way. But the universe does not need familiarity to move forward. It changes because the laws of physics demand it. In the silent era, time was not measured by light crossing space, but by space itself changing shape. It was not marked by events, but by conditions. Eventually, those conditions would allow new forms of structure, neutral atoms, transparent space, long journeys of light. With those came new clocks. Stars would burn at predictable rates, galaxies would rotate, planets would orbit, time would become visible. But here, before all of that, time was invisible yet absolute in its effect. The universe grew older with every expansion, even though nothing could yet reflect that age back to itself. This reminds us that time does not depend on observation. It does not wait to be noticed. It passes because change occurs. And perhaps that is the most calming thought of all. Even in total darkness, even without witnesses, the universe moved forward gently, steadily, without hesitation. As the silent era continued, one final transition approached. A moment when time would leave behind a visible imprint that still surrounds us today. And as we move into the next part of this quiet journey, one question remains. What happened when the universe cooled enough for atoms to finally form? Part 5. The quiet cooling that changed everything. As the universe expanded, it cooled, slowly, almost imperceptibly. This cooling allowed protons and electrons to begin forming stable atoms for the first time. Hydrogen emerged, helium followed. This process, known as recombination, did not produce light, but it removed the barriers that had trapped it. The fog began to thin. For hundreds of thousands of years, nothing about the universe seemed ready to change. Expansion continued, temperatures dropped, but the plasma state held firm. Electrons remained too energetic to settle. Protons remained exposed. Photons continued their endless scattering. From the outside, if such a perspective were possible, the universe appeared locked in sameness. But physics is patient. Cooling does not announce itself. It does not arrive suddenly. It accumulates quietly, degree by degree, interaction by interaction. Eventually, a threshold is crossed, not through force, but through inevitability. As the universe cooled to around 3,000 degrees Kelvin, conditions shifted. Electrons, which had once moved too quickly to remain bound, began to slow. Protons, positively charged and waiting, could finally capture them. For the first time since the earliest moments after the Big Bang, stable atoms could exist. This was not a dramatic event. There was no flash, no wave of light sweeping through space. Recombination happened gradually, everywhere, almost uniformly. Hydrogen atoms formed first, the simplest and most abundant element. Helium followed shortly after, capturing its own electrons into stable configurations. The name recombination is a little misleading. It suggests something returning to a previous state. In truth, this was the first time atoms ever existed. It was a beginning, not a return. With the formation of neutral atoms, something fundamental changed. Electrons were no longer free to scatter photons endlessly. Once bound to nuclei, electrons became far less effective at blocking light. Space, which had been opaque for so long, began to lose its grip on photons. The fog did not vanish instantly, it thinned. Gradually, steadily, the universe transitioned from opaque to transparent. Photons that had been trapped since the earliest moments were suddenly free to travel vast distances without interruption. This moment marks one of the most important transitions in cosmic history. It did not create light. Light already existed. What it created was freedom. For the first time, light could move. As photons streamed outward, they carried with them information about the state of the universe at that precise time. The temperature, the density, the tiny fluctuations seeded long ago. This released light filled all of space, expanding outward as the universe continued to stretch. Today, we observe this ancient release as the cosmic microwave background. It surrounds us in every direction, a faint uniform glow cooled by billions of years of expansion. It is the oldest light we can see, a fossil from the moment the universe became transparent. But here, in this part of the story, we are standing at the edge of that transition. The fog is thinning, but the universe is still quiet. Stars have not formed, galaxies do not yet exist. Light can travel, but it has nowhere interesting to come from. The universe is now transparent, but still dark. This distinction matters. Transparency allows visibility, but it does not guarantee illumination. Light can move, but without sources, there is nothing to see. After recombination, the universe entered a new kind of darkness, one defined not by trapped light, but by the absence of light-producing objects. This quiet period would last hundreds of millions of years. As you rest now, breathing slowly, it may help to imagine this transition not as an event, but as a soft release. The universe did not burst into clarity. It exhaled. A long-held tension eased. Photons drifted outward, cooling, stretching, becoming gentler with every passing moment. Meanwhile, gravity continued its work. The same tiny density fluctuations that existed before recombination now had new freedom. Without radiation pressure constantly pushing back, matter could collapse more easily. Regions that were slightly denser than average began to grow denser still. Gas slowly gathered. The seeds of stars were planted. This is another quiet truth of cosmology. Light does not create structure. Gravity does. Recombination removed an obstacle, allowing gravity to act more efficiently. In the darkness that followed, structure began to take shape. Hydrogen atoms, now neutral, could clump together without being torn apart by energetic photons. Cooling continued. Gas clouds thickened. Over immense spans of time, they would collapse under their own weight, igniting the first stars. But that ignition lay far in the future. Here, the universe rested in a delicate balance, transparent but unlit, calm but pregnant with possibility. The simplicity of this era is striking. The universe consisted almost entirely of hydrogen and helium. No heavier elements existed yet. No carbon, no oxygen, no iron. Those would only appear after generations of stars lived and died. Everything complex was still waiting, and yet everything necessary was already in place. The laws of physics did not change. Gravity behaved as it always had. Electromagnetism governed interactions. Expansion continued at its steady pace. From these simple ingredients, everything else would eventually emerge. There is something deeply soothing about this moment in cosmic history. The universe had done all the hard work. It had cooled, simplified, stabilized. Now, it could afford to wait. As you lie still, letting your thoughts slow, consider how much of reality depends on patience. Stars require millions of years to form. Galaxies require billions. Even the universe itself did not rush toward complexity. Recombination was not the end of darkness, it was the end of confinement. It allowed light to move freely, but it did not yet give light a voice. That voice would come later, when the first stars ignited, when nuclear fusion began to shine across space. But before that brilliance, there was this long, gentle pause. A universe transparent and silent. Modern instruments allow us to study recombination with astonishing precision. Satellites have measured the cosmic microwave background down to variations of millionths of a degree. From this data, scientists reconstruct the exact conditions of the universe when atoms first formed. The agreement between theory and observation is one of the great triumphs of modern science. It tells us that this quiet cooling really happened, that the fog really thinned, that the universe truly did move from opacity to openness through nothing more dramatic than expansion and patience. As you breathe in, then slowly out, remember that this story is not about spectacle. It is about inevitability. about laws playing out over time, about change so gradual that it can only be seen from billions of years away. The quiet cooling that changed everything did not feel important at the time. There was no one to notice it, no marker in the sky, no sudden transformation, and yet, without it, nothing visible today could exist. Every star, every planet, every living thing owes its existence to this subtle shift. The moment electrons finally settled down, the moment space let light go. As the universe entered its next long chapter, transparent but dark, another question began to take shape. If light was finally free, why did the universe remain dark for so long afterward? Part 6. The moment the universe became transparent. About 300,000 years after the Big Bang, a subtle transition occurred. Photons were finally able to travel freely through space. Light was released, not as stars or suns, but as a uniform glow in every direction. That light still exists today as the cosmic microwave background, a faint afterglow that fills the universe and marks the end of total darkness. This moment did not arrive with spectacle. There was no sudden flash, no dividing line between before and after. The universe did not light up in the way we instinctively imagine illumination. Instead, transparency arrived quietly, the way clarity often does, without announcement. For hundreds of thousands of years before this moment, photons had existed, but were imprisoned. They scattered endlessly off free electrons, unable to move more than a microscopic distance without being redirected. Space was bright, yet sealed. When electrons finally settled into stable orbits around nuclei, that barrier dissolved. With electrons bound into neutral atoms, the universe changed its behavior toward light. Photons no longer encountered constant resistance. For the first time, they could travel in straight lines across expanding space. Light was set free. Every photon released at that moment carried information, not a message written in symbols, but a physical record of the universe's temperature, density, and structure at that time. These photons spread outward in all directions, filling the cosmos evenly, their wavelengths stretching as space itself expanded. At the moment of release, this light was not microwave radiation. It glowed faintly orange, comparable to the warmth of a dim ember. Over billions of years, as the universe expanded by enormous factors, that light cooled. Its wavelengths lengthened. Today, it resides in the microwave portion of the spectrum, invisible to human eyes but detectable with precise instruments. This is the cosmic microwave background, often abbreviated as the CMB. It is not a distant object. It surrounds you completely. Every direction you look, every empty space between stars and galaxies is filled with this ancient light. It is the oldest light we can ever observe. What makes this moment so extraordinary is not just that light was released, but that it has been traveling ever since, uninterrupted. No other signal in the universe has had such a long, continuous journey. Every star's light eventually fades, scatters, or is absorbed. The CMB has persisted, quietly cooling, quietly expanding for nearly 14 billion years. When scientists first detected it in 1965, it was an accident. Two radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate noise from their antenna. No matter where they pointed, a faint background hiss remained. It came from everywhere equally. They had stumbled upon the echo of the universe becoming transparent. That discovery confirmed decades of theoretical prediction. Cosmologists had calculated that if the universe began hot and dense, it should leave behind a relic glow. The CMB was that glow, finally observed. But here, in this quiet chapter of the story, we are not focused on discovery. We are focused on what the moment meant for the universe itself. Transparency changed the rules. Before this moment, matter and radiation were tightly coupled. Light pushed back against gravity. Pressure resisted collapse. After transparency, radiation lost its grip. Matter could move more freely under gravity's influence. This did not create stars immediately, but it allowed the universe to begin separating into regions. Dense areas slowly grew denser. Empty areas grew emptier. Structure was no longer smoothed out by trapped radiation. In this way, transparency marked the end of one era, and the opening of another. The universe had shifted from a glowing fog to a clear, dark expanse. It is important to pause on that word, dark. Even after light was released, the universe did not become bright. There were still no stars, no galaxies, no luminous objects. The cosmic microwave background itself was uniform and faint. To any hypothetical observer, the universe would still appear dark, even though light could now travel freely. This is one of the great ironies of cosmology. The moment light was liberated did not bring illumination. It brought silence. The universe entered what scientists call the cosmic dark ages, not because light was trapped, but because no new light sources existed yet. The background glow faded steadily as space expanded, leaving the universe transparent but unlit. As you breathe gently now, imagine this moment, a universe finally clear, finally open, yet still empty of stars. Space stretched endlessly, filled with neutral hydrogen, cooling quietly, waiting. The cosmic microwave background itself carries subtle variations, tiny differences in temperature on the order of 1 part in 100,000. These variations are not noise. They are the fingerprints of the universe's earliest structure. They show where matter was slightly denser, where gravity would later pull harder. Every galaxy, every cluster, traces its lineage back to these faint ripples frozen into light. In this sense, the CMB is not just a photograph, it is a blueprint. When modern satellites map it, they are not simply looking at radiation, they are reading the universe's earliest conditions, preserved with astonishing fidelity. The patterns match theoretical predictions with remarkable precision, confirming that the universe evolved according to simple, consistent laws. But for the universe itself, this moment was not about confirmation, it was about release. For the first time, space allowed distance to matter. Light could travel long enough to create perspective. Near and far could exist. Information could move. Yet nothing was there to observe it. This may be one of the most humbling ideas in science. The universe became observable long before observers existed. It prepared the stage patiently, long before any actors arrived. As the CMB streamed outward, it carried with it the last whisper of the universe's earliest heat. Over time, that whisper softened. Today, it rests at a temperature just above absolute zero, a gentle hum permeating all of space. Even now, as you lie still, this ancient light passes through your body without notice. It does not warm you. It does not illuminate your room. But it is there, a reminder that transparency came before brilliance. This moment also set a limit on what we can ever see. We cannot observe earlier times directly with light, because before transparency, photons could not travel freely. The cosmic microwave background is the farthest back we can look using electromagnetic radiation. Beyond it lies opacity. Beyond it lies silence. This boundary is not arbitrary. It is written into the physics of atoms and light. It tells us that some parts of cosmic history will always remain hidden, not because they did not exist, but because the universe was not yet ready to reveal them. There is something quietly comforting in that limit. The universe does not give up all its secrets at once. It reveals them slowly, in layers, as conditions allow. The moment the universe became transparent was not the birth of light, but the birth of visibility. It allowed the universe to begin telling its story through radiation, even if no one was yet listening. And as the cosmos drifted forward into its long, starless night, another question naturally arises. If the universe could finally be seen, why did it remain dark for so long afterward? Part 7. Why darkness returned after the first light. Paradoxically, after the universe became transparent, it entered another dark age. The released light stretched into microwaves as space expanded, becoming invisible to human eyes. Stars had not yet formed, galaxies did not exist. The universe was once again dark, not because light was trapped, but because no new light sources had ignited. This second darkness was different from the first. Before transparency, light had been confined, scattered endlessly by plasma. Now, light was free, but fading. The universe had opened its doors, only to find there was very little to illuminate what lay inside. When the cosmic microwave background was released, it carried the warmth of a young universe. But expansion is relentless. As space stretched, every wavelength of that ancient light stretched with it. What began as a faint visible glow cooled steadily, slipping out of the visible spectrum, becoming infrared, then microwave. The universe did not turn off the light. It diluted it. In this newly transparent cosmos, there were no stars to replace that fading glow, no nuclear furnaces burning hydrogen into helium, no galaxies gathering billions of suns into shining spirals. The universe had matter and space, but not yet light-making engines. This era is known as the Cosmic Dark Ages. It is tempting to imagine darkness as a pause, a waiting room between important events. But the Dark Ages were not empty. They were busy, subtle, and essential. Gravity was working quietly, drawing matter together in places where density was just slightly higher than average. These regions were invisible, but they were growing. As you lie still now, it may help to picture this darkness not as absence, but as preparation. A long night before dawn, the universe had laid its foundations. Now it needed time. The matter-filling space was mostly neutral hydrogen with traces of helium. These atoms drifted slowly, responding to gravity's pull. Where dark matter had already formed invisible scaffolds, ordinary matter followed, falling inward, thickening, cooling further. But collapse is not instant. Gas resists compression. Heat builds as matter falls inward, slowing the process. In a universe without heavy elements to radiate energy efficiently, cooling was slow. The first structures formed reluctantly over tens and hundreds of millions of years. During this time, the universe had depth for the first time. Distances mattered. Light could travel. But there were no beacons, no points of reference, no way for an observer, if one existed, to orient themselves. The darkness was vast, but not chaotic. It was governed by equations. Gravity obeyed the same laws it always had. Expansion continued at a predictable rate. Tiny fluctuations grew steadily, amplified by time. This second darkness is often overlooked because it left fewer direct traces. Unlike the cosmic microwave background, which preserved a snapshot of transparency, the Dark Ages left their imprint indirectly. In the distribution of galaxies, in the large-scale structure of the universe, in the timing of the first stars. Modern telescopes are beginning to probe this era through subtle signals, such as the faint absorption of background radiation by neutral hydrogen. These measurements suggest a universe slowly transitioning, inch by inch, toward illumination. But for most of this era, the universe would have appeared almost completely black. Not empty black, but deep, silent black. The kind of darkness where space itself feels present, where matter exists without announcing itself, where motion happens without light to trace it. There's a quiet poetry to this stage of cosmic history. The universe had learned to let light go, but it had not yet learned how to make it again. The first stars required special conditions. Gas needed to collapse enough to trigger nuclear fusion. Temperatures in the core had to reach millions of degrees. Without heavier elements to help radiate heat away, the first stars grew massive, unstable, and rare. Until those conditions were met, darkness prevailed. And yet, this darkness was productive. It allowed gravity to work without interference. Radiation pressure, which had smoothed out variations before transparency, was gone. Now matter could clump more effectively. Structures grew sharper, differences deepened. In this sense, darkness was an ally. As you breathe slowly, notice how stillness can feel active, how silence can feel full. The cosmic dark ages were like that, a universe holding its breath. Time continued to pass, measured by expansion and collapse. Hundreds of millions of years slipped by. The universe aged quietly, unseen. Eventually, in the densest regions, the first stars ignited. When they did, they shattered the darkness locally. Their ultraviolet light reionized the surrounding hydrogen, carving out bubbles of illumination in the neutral fog. But that is the next chapter. Here, in this part, we remain in the second darkness, a universe transparent but unlit, clear but quiet. This era reminds us that light is not guaranteed. It must be earned through complexity, through structure, through the slow work of gravity. The universe did not rush toward brightness. It allowed darkness to do its work first. Even today, vast regions of space remain dark, far from any star. The night sky we see is punctuated by light, but mostly empty. In many ways, the Dark Ages never fully ended. They were simply interrupted. When we look between galaxies, into the deepest voids, we are glimpsing a faint echo of that ancient darkness. Space where light passes through, but little originates. The universe, it seems, is comfortable with darkness. It uses it as a backdrop, a canvas on which light can eventually stand out. As this long night continued, something subtle but decisive was approaching. Gravity was winning its slow contest. Gas clouds were nearing the point of ignition. The first stars were almost ready. And when they arrived, they would not just add light, they would change the chemistry of the universe forever. But before that transformation, the universe rested in darkness once more. Not trapped, not opaque, simply waiting. As we continue this quiet journey, one question begins to glow faintly in the distance. What finally broke the silence of the cosmic dark ages? Part 8. The long cosmic night before the first stars. This second darkness lasted hundreds of millions of years. During this time, gravity quietly worked, pulling slightly denser regions of gas together. Hydrogen clouds slowly collapsed, growing warmer and denser. No explosions, no sudden brightness, just patience written into the laws of physics. After the universe became transparent, it did not rush toward illumination. Instead, it entered a long, steady night. Space was clear but empty of light. Matter drifted in vast, cold expanses, responding only to the faint, persistent pull of gravity. If the earlier darkness was caused by confinement, this one was caused by absence. Gravity, unlike light, does not announce itself. It does not flash or flare. It acts silently, steadily, across immense distances. During this cosmic night, gravity was the only force shaping the future in visible ways. Wherever gas was just slightly denser than average, gravity pulled a little harder. Over time, that small advantage grew. These regions did not collapse quickly. Gas resists compression. As hydrogen clouds fell inward, they heated up. That heat pushed back, slowing further collapse. Without heavier elements to radiate energy efficiently, cooling was difficult. The universe, still chemically simple, made structure slowly. This slowness is essential to understand. From a human perspective, hundreds of millions of years feels impossibly long. From a cosmic perspective, it was necessary. The universe needed time to settle, to allow gravity to overcome pressure without tearing matter apart. As you rest now, breathing gently, it may help to imagine this process not as motion, but as gathering. Like fog slowly thickening in a valley. Almost imperceptible at first, but inevitable. Dark matter played a quiet but crucial role during this era. Invisible and non-interacting with light, it had already formed vast halos, regions where gravity was slightly stronger. Ordinary matter, the hydrogen and helium left after recombination, followed these invisible structures, drifting inward, guided by forces it could not see. This partnership shaped the universe's future. Dark matter provided the framework. Normal matter provided the substance. Together, they built the scaffolding of galaxies long before any star would shine. Still, everything remained hidden. There were no sparks, no flashes of ignition, just clouds growing thicker, denser, warmer. In the densest cores, temperatures climbed slowly. Pressure increased. Atoms collided more frequently. But fusion, the process that powers stars, remained out of reach. Fusion requires extremes, millions of degrees, enormous pressure, conditions the early universe could not reach easily. Only in the most massive collapsing clouds did gravity eventually win. During this time, the universe was quiet in a way we rarely experience. Not silent because nothing happened, but silent because change was gradual and uniform. There were no sudden events to break the calm. This long night shaped the character of the first stars. Because cooling was inefficient, early gas clouds grew very large before collapsing fully. When fusion finally ignited, It did so in massive stars, many times larger than our sun. These stars lived fast and died young, burning bright and briefly, but they were still far away. Here, in this part of the journey, the universe is still waiting. Time continued to pass, marked only by expansion and slow collapse. The cosmic background cooled further, becoming ever more faint. The temperature of space dropped from thousands of degrees to just a few dozen above absolute zero. In this environment, chemistry was simple. Hydrogen dominated, helium followed. There were no molecules, no dust grains, no complex structures to accelerate cooling. Everything was elemental. And yet, this simplicity was powerful. It meant that the universe's evolution was clean, governed by a small set of rules applied consistently everywhere. Gravity pulled, pressure resisted, expansion stretched space over and over again. As you listen, it's worth noticing how often patience appears in nature. Mountains rise over millions of years, continents drift slowly. Even life evolves through countless small changes. The universe itself followed this pattern. The cosmic night was not wasted time, it was necessary time. In modern cosmology, this era is one of the hardest to observe directly. There is little light to detect, no bright objects to study. But scientists are beginning to listen for faint signals, such as the interaction between neutral hydrogen and background radiation. These signals whisper clues about the universe's long night. From these measurements, we know that the first stars likely formed around 100 to 200 million years after the Big Bang. But before that, there was nothing to see. Only matter gathering in the dark. If you could somehow float through this universe, which again you cannot, but if you could, you would see no stars, no galaxies, no glowing clouds, just darkness and depth. Space would feel vast in a way it never quite does now, because there would be nothing to interrupt it. And yet, that emptiness was deceptive. It was full of potential. The first stars were inevitable, not miraculous. Given enough time, gravity always finds a way. The laws of physics do not require urgency. They operate until conditions are met. This long night teaches us something subtle about beginnings. They are often preceded by long periods of quiet preparation. The universe did not burst into light immediately. It allowed itself to mature. As gas clouds grew denser, their cores slowly approached the temperatures needed for fusion. When hydrogen nuclei finally began to merge, releasing energy, the balance changed. Pressure from fusion pushed outward, countering gravity. A star was born. But again, that moment lies just ahead. Here, in the cosmic night, the universe is still dark, still patient, still gathering. As you breathe out, letting your body relax further, consider how much of reality unfolds this way. Not through sudden transformation, but through accumulation, through thresholds crossed quietly, without fanfare. The long cosmic night before the first stars was not an absence of activity. It was activity without spectacle, a universe becoming ready. And as gravity continued its gentle work, another question slowly took shape. What happens when the first stars finally ignite and darkness is broken for the first time? Part 9. How gravity learned to sculpt structure. Tiny irregularities left over from the early universe became seeds. Where matter was just a little denser, gravity pulled harder. Over immense spans of time, these regions deepened, drawing in surrounding gas. The universe began to develop structure, though still hidden in darkness. At first, these irregularities were almost nothing. Differences in density so small they amounted to variations of less than 1 part in 100,000. In any everyday sense, they were meaningless. But gravity is patient, and it never forgets an advantage, no matter how slight. From the earliest moments after the Big Bang, space was not perfectly smooth. Quantum fluctuations, stretched to cosmic scales during inflation, left faint imprints in the distribution of energy. These imprints survived every transition that followed. They passed through the era of plasma. They endured recombination. And in the darkness, after transparency, they finally began to matter. Gravity responds only to mass and energy. Where there was slightly more, gravity pulled slightly harder. That extra pull attracted more matter, increasing the mass and strengthening the pull further. This feedback loop is simple, but relentless. Over millions of years, tiny differences became meaningful contours. This is how structure begins, not through sudden creation, but through amplification. As you lie still now, it may help to imagine this process as a whisper becoming a murmur, a barely noticeable slope slowly steepening. Nothing dramatic happens at first, but time multiplies small effects. In the early universe, gravity faced competition, radiation pressure pushed back against collapse, expansion stretched space apart, but after transparency, radiation loosened its grip. Matter was finally free to respond more fully to gravity's call. Dark matter played a central role in this stage. Unlike ordinary matter, dark matter does not interact with light or radiation. It does not heat up easily. It does not feel pressure in the same way gas does. This made it exceptionally responsive to gravity. While normal matter struggled to cool and collapse, dark matter moved ahead, clumping early and efficiently. It formed vast invisible halos, regions where gravity was already stronger long before stars existed. These halos became the universe's hidden skeleton. Ordinary matter followed. Hydrogen. Gas drifted inward, guided by gravitational wells it could not see. Slowly, gas collected in these regions, thickening, heating, and beginning the long process toward star formation. But even now, everything remained unseen. Structure existed, but it did not shine. This stage of cosmic evolution reminds us that visibility is not the same as existence. Galaxies were being shaped before they ever glowed. The universe was building its architecture in silence. As gravity sculpted matter, it created a web-like pattern on the largest scales. Filaments of matter stretched across space, intersecting at dense nodes. Vast voids opened between them. This cosmic web still defines the large-scale structure of the universe today. Modern simulations show this process in remarkable detail. Starting from the tiny fluctuations measured in the cosmic microwave background, computers evolve gravity forward in time. The resulting structures match what we observe in the distribution of galaxies billions of years later. This agreement tells us something profound. The universe did not improvise. It followed a plan written in its earliest moments. Gravity did not need to learn new rules. It simply needed time. At smaller scales, within growing halos, gas dynamics became increasingly complex. As matter fell inward, it heated up. Heat resisted further collapse. Cooling became the limiting factor. Without heavy elements to radiate energy efficiently, gas could only cool through simple atomic processes. This slowed everything down. But slowness did not stop progress. It shaped it. Regions that could cool slightly faster collapsed sooner. These regions would host the first stars. Others lagged behind. Structure did not form everywhere at once. It emerged unevenly, guided by the subtle differences imprinted at the beginning. This unevenness is essential. It created diversity. Some regions became rich in stars and galaxies. Others remained sparse, forming the vast cosmic voids we see today. As you listen, consider how familiar this pattern is. Small differences, given enough time, lead to very different outcomes. The universe reflects this principle at every scale. In the darkness of this era, gravity worked without distraction. There was no feedback from starlight, no explosions to disrupt collapse. The universe was quiet enough for structure to settle into place. This quiet did not last forever. Once the first stars ignited, their light and energy would begin to reshape their surroundings. Radiation would heat gas, slowing collapse in some regions while triggering it in others. Supernovae would stir matter violently. But before all of that, gravity had its moment, a long, uninterrupted period to sculpt the universe's basic form. Even today, gravity remains the dominant architect of cosmic structure. Galaxies orbit within clusters. Clusters fall along filaments. Everything traces back to this early era when gravity began amplifying tiny imperfections into lasting form. It is worth noting how little was required. No guiding hand, no external influence. Just simple laws applied consistently across vast stretches of time and space. The universe did not need complexity to create complexity. It needed patience. As you breathe slowly, allowing your thoughts to soften, imagine this hidden construction. Invisible frameworks forming in darkness, matter flowing gently into place, a universe assembling itself long before it could be admired. This part of the story is a reminder that much of reality unfolds beyond perception. What we see is only the illuminated surface of deeper processes. Gravity learned to sculpt structure, not by adapting, but by enduring. It worked with what it was given: small differences, immense time. And from that combination, everything familiar emerged. As this silent shaping continued, another transformation approached, one that would finally bring light back into the universe in a new way. And as we continue this quiet journey, one question remains. When structure was finally in place, what was the first thing to shine within it? Part 10. When darkness shaped the first galaxies. Before galaxies shone, they existed as invisible frameworks of dark matter and gas. These early halos guided the flow of normal matter, shaping where stars would one day ignite. Long before anything could be seen, the architecture of the cosmos was already under construction. Galaxies did not begin as islands of light. They began as regions of gravity. Vast, unseen concentrations of dark matter formed first, gathering quietly out of the primordial universe. These halos did not glow, reflect, or emit. They announced their presence only through their pull. And yet, they would determine nearly everything that followed. Dark matter outweighs ordinary matter by more than 5 to 1. It does not interact with light, but it interacts strongly with gravity. In the early universe, this made it the primary sculptor of structure. While gas struggled to cool and collapse, dark matter clumped efficiently, forming the first stable gravitational wells. You can imagine these halos as gentle depressions in the fabric of space, not sharp pits, but broad, patient valleys. Ordinary matter, drifting through the universe as neutral hydrogen and helium, felt these depressions and slowly flowed inward. This flow was not dramatic. There were no streams of fire or glowing arcs. Gas moved quietly, guided by gravity alone. Over time, these halos accumulated more and more matter, becoming deeper and more influential. This is how the first galaxies were outlined in darkness. Within each halo, gas began to settle toward the center. As it fell inward, it heated up. Heat resisted collapse, slowing the process. Without heavy elements or dust to help radiate energy away, cooling was inefficient. Gas lingered in a delicate balance between falling inward and pushing outward. This balance shaped the nature of early galaxies. They did not form quickly. They assembled piece by piece over hundreds of millions of years. Gravity pulled, pressure resisted, expansion stretched space. The universe negotiated with itself. As you lie still now, it may help to imagine this negotiation happening everywhere at once. Countless halos forming across the cosmos, each one tracing a possible future galaxy. Most still dark, all still silent. These early halos varied in size. Some were small, destined to host only a few stars or none at all. Others grew larger, merging with neighboring halos, building up mass through slow gravitational encounters. These mergers were common. The universe was young, crowded, and dynamic. When halos merged, their dark matter cores combined, deepening the gravitational well. Gas followed, though not always smoothly. Shock waves formed as clouds collided. Turbulence stirred the gas, redistributing energy and momentum. Still, nothing shone. The first galaxies were not spiral or elliptical in any familiar sense. They were irregular, clumpy, chaotic collections of gas bound together by gravity. Their shapes were defined more by motion than by form. Yet even in this chaos, patterns emerged. The cosmic web, with its filaments and nodes, funneled matter into growing halos. Galaxies formed preferentially at intersections where filaments met and gravity was strongest. This large-scale structure is still visible today. When astronomers map the distribution of galaxies, they see the same web-like pattern predicted by simulations of dark matter evolution. The visible universe traces an invisible framework laid down in darkness. What is remarkable is how early this framework formed. Long before the first stars ignited, long before light could reveal structure, the universe had already decided where galaxies would live. Darkness was not merely a backdrop, it was an architect. As gas continued to collect in these halos, conditions slowly approached a tipping point. In the densest regions, cooling became just efficient enough for collapse to accelerate. Gas clouds fragmented. Smaller clumps formed within larger ones. These clumps were the direct ancestors of stars. But still, galaxies existed before stars. They were defined by gravity, not by light. Their mass, motion, and future were set before their first glow. This sequence matters. It tells us that galaxies are not collections of stars that happen to gather together. They are gravitational entities first, luminous entities second. Even today, galaxies retain massive dark matter halos far larger than their visible components. Stars orbit within these halos, held together by gravity that cannot be seen. When we look at a galaxy, we see only a small fraction of its true mass. During this early era, gas within halos began to settle into rotating structures. As matter fell inward, it conserved angular momentum, causing it to spin faster. This rotation laid the groundwork for disks, though early disks were thick, turbulent, and unstable. Rotation added another layer of structure. It prevented total collapse, spreading gas into flattened shapes. These rotating systems would later evolve into the familiar spiral galaxies we see today. But again, this happened in darkness. As the universe aged, halos grew, merged, and matured. Some became hosts to the first stars, others remained starless, perhaps forever. The universe did not guarantee illumination to every structure it built. There is something quietly humbling about that. Existence does not require expression. Many things form, persist, and dissolve without ever being seen. As you breathe slowly, letting your body relax, consider how much of reality is like this. Foundations laid quietly, structures built without applause, meaning existing without display. When the first stars finally ignited within these early galaxies, they did not illuminate everything at once. They lit small pockets of space, carving bubbles of ionized gas within the surrounding darkness. Light returned gradually, unevenly. But before that first spark, galaxies already existed as gravitational truths. This challenges how we often think about beginnings. We imagine light as the start of things. In reality, light is often the reveal, not the creation. The universe built its cities before turning on the lights. As this era continued, galaxies became more complex. Gas cooled more efficiently in some regions. Star formation began to accelerate. Feedback from the first stars would soon reshape their host galaxies, enriching them with heavier elements. But that is the next stage of the story. Here, in this part, we remain with galaxies still unborn in light but fully present in gravity. Vast structures traced in darkness, waiting patiently for their first glow. And as this hidden architecture solidified, another question gently emerges. When the first stars finally ignited inside these dark galaxies, how did their light change the universe forever? Part 11. The first stars as endings, not beginnings. The ignition of the first stars did not start the universe's story. It ended a long silence. When nuclear fusion finally began inside collapsing gas clouds, light returned to the cosmos in scattered points. These stars were massive, short-lived, and violent, breaking the darkness that had lasted for hundreds of millions of years. For so long, everything had been preparation, expansion, cooling, gathering. The universe had waited patiently, assembling the conditions required for something new. When the first stars finally ignited, they did not arrive as a gentle dawn. They arrived as interruptions. These earliest stars, often called population 3 stars, were unlike anything that exists today. They formed in a universe made almost entirely of hydrogen and helium. No carbon, no oxygen, no iron. None of the elements that modern stars rely on to regulate their behavior. Because of this chemical simplicity, the first stars grew enormous. Gas clouds collapsed without efficient, cooling pathways. Instead of fragmenting into many small stars, they tended to form a few very large ones. Some may have been tens or even hundreds of times the mass of our sun. They burned hot, bright, and fast. But before they burned, there was a long approach. Gravity pulled gas inward until the core temperature reached millions of degrees. At that threshold, hydrogen nuclei began to fuse into helium. Energy was released, pressure surged outward, collapse halted. A star was born. This moment did not happen everywhere at once. It happened sporadically, wherever conditions were right. The universe did not light up uniformly. It flickered. Each new star carved out a small island of light within the vast darkness. Their ultraviolet radiation flooded nearby space, ionizing the surrounding hydrogen. The neutral fog that had filled the universe for so long began to retreat locally, bubble by bubble. This was the beginning of reionization, a process that would eventually transform the entire cosmos. But here, at the very start, the universe remained mostly dark, punctuated by rare, intense points of light. The first stars lived brief lives. Their enormous masses made them unstable. They burned through their fuel rapidly, shining millions of times brighter than the sun, but lasting only a few million years. In cosmic terms, they were fleeting. When they died, they did not fade quietly. Many ended their lives as supernovae, violent explosions that scattered newly forged elements into space. Others may have collapsed directly into black holes, leaving behind no explosion at all, only silence and gravity. But either way, they changed the universe permanently. For the first time, elements heavier than helium existed: carbon, oxygen, nitrogen. The raw materials for planets, chemistry, and eventually life were created inside these stars and released when they died. In this sense, the first stars were endings. They ended the era of elemental simplicity. They ended the universe's long chemical innocence. They also ended the pure darkness. Light had existed before, but now it had sources, direction, contrast. The universe could finally be seen, even if no eyes yet existed to see it. As you breathe slowly now, consider how rarely beginnings are truly beginnings. More often, they are thresholds, points where quiet accumulation becomes visible, change. The first stars did not appear suddenly. They emerged after hundreds of millions of years of slow preparation. Their ignition was not a creation from nothing. It was the release of stored potential. And their impact extended far beyond their brief lives. Their radiation altered the surrounding gas, heating it, ionizing it, changing how matter could collapse in the future. In some regions, star formation was suppressed. In others, shock waves triggered new collapse. Light reshaped the darkness in complex ways. This feedback introduced a new kind of time into the universe. Before stars, evolution was smooth and predictable. After stars, it became dynamic, uneven, and energetic. Explosions, radiation, and motion added complexity. The universe became louder, but even this loudness was built on silence. It is easy to imagine the first stars as heroic pioneers, lighting the way forward, but they were also destructive. Their radiation stripped electrons from atoms. Their explosions tore gas clouds apart. They erased as much as they created. This dual nature is fundamental to cosmic evolution. Creation and destruction are inseparable. New structure often requires old structure to be broken. The first stars also marked the beginning of history that could be remembered. Their light traveled across space, carrying information. Some of that light still travels today, stretched and redshifted, waiting to be detected by telescopes. In principle, the light from the very first stars may still be out there, diluted beyond easy detection, but not erased. The universe does not forget easily. And yet, despite their importance, the first stars were rare. Most of the universe remained dark long after they appeared. Reionization was a slow, uneven process. Bubbles of ionized gas grew, merged, and expanded over hundreds of millions of years. Darkness did not vanish all at once. It retreated gradually. As you lie still now, you can imagine these first stars as distant campfires in a vast night, small, intense, temporary, their warmth reaching only so far. Over time, more stars formed, galaxies grew richer, heavy elements accumulated, cooling became more efficient, star formation accelerated. the universe transitioned from rarity to abundance. But that abundance rests entirely on these first endings. The first stars ended the cosmic dark ages. They ended the universe's chemical simplicity. They ended the era where gravity worked alone. They introduced light as an active force, not just a background glow. And yet, they did not bring immediate comfort or order. Their universe was harsh, unstable, and violent. It would take billions more years for calmer systems like our sun to form. This reminds us that progress is not smooth. The universe did not move from darkness to balance in a single step. It passed through extremes. As you exhale, letting your body sink deeper into rest, notice how this mirrors so much of existence. Growth often begins with disruption. Change often arrives through intensity. The first stars were not gentle guides. They were brief, blazing interruptions in an ancient silence. But without them, nothing familiar could exist. Every atom of carbon in your body, every atom of oxygen you breathe, every iron atom in your blood traces its ancestry back to stars. And the very first of those stars began not a story, but ended a long, quiet chapter. As their light spread and their influence grew, the universe entered a new phase, one where light and matter interacted in complex, evolving ways. And as we continue this quiet journey, one final question lingers. How did the universe change once light became a permanent presence rather than a fleeting interruption? Part 12. How light permanently changed the universe. Once stars existed, they transformed their surroundings. Ultraviolet radiation stripped electrons from atoms, reheating and reionizing the universe. Space became transparent again, this time permanently. Light could now travel across cosmic distances, carrying information, structure, and history. When the first stars ignited, they did more than glow. They altered the fundamental state of the universe. Their light did not simply illuminate space, it interacted with it, reshaped it, and rewrote the conditions under which matter could exist. The darkness that had defined the long cosmic night was not removed gently. It was dismantled. The earliest stars emitted intense ultraviolet radiation, far more energetic than the light produced by stars like our sun. This radiation carried enough energy to strip electrons from neutral hydrogen atoms, returning them to an ionized state. In doing so, the stars reversed part of what recombination had accomplished hundreds of millions of years earlier. This process is known as reionization. It did not happen instantly, and it did not happen everywhere at once. Each star carved out a growing bubble of ionized gas around itself, a region where atoms were once again separated into charged particles. These bubbles expanded outward, overlapping with others as more stars formed. Over time, the universe transitioned from mostly neutral back to mostly ionized. This might sound like regression, but it was transformation. The universe did not return to its original opaque plasma state. The density was now far lower. Space had expanded enormously. Even when ionized, matter no longer trapped photons as it once had. Light remained free. Transparency, once achieved, was never lost again. This marked a profound turning point. For the first time, the universe became permanently observable. Light could travel across billions of light years without being scattered or confined. Information could persist. History could be carried forward. Before this era, the universe had moments of visibility. Now, it gained memory. Every star that formed added to this transformation. Galaxies grew brighter. Their combined radiation accelerated reionization, pushing ionized regions farther into the surrounding darkness. Eventually, the bubbles merged, and the last pockets of neutral hydrogen were exposed to starlight. The universe crossed a threshold. Darkness no longer dominated. As you rest now, breathing slowly, imagine this change not as a sudden blaze, but as a slow dawn spreading unevenly across a vast landscape. Light advanced gradually, reclaiming space, redefining what the universe could be. This new transparency changed how matter behaved. Ionized gas interacts differently with gravity and radiation than neutral gas does. Heating from starlight prevented some regions from collapsing. Further, while shock waves and pressure gradients triggered collapse elsewhere. Star formation became regulated rather than purely gravitational. Light introduced feedback. This feedback is one of the most important drivers of cosmic evolution. Stars heat their surroundings, slow the formation of nearby stars, enrich space with heavy elements when they die, and stir gas through winds and explosions. Each generation of stars inherits the conditions shaped by the previous one. The universe became self-modifying. With permanent transparency, light also became a messenger. Photons traveled across cosmic distances, carrying images of distant objects into the future. When we look at galaxies billions of light years away, we are seeing them as they were billions of years ago. Light turned space into an archive. Before this era, the universe could not preserve visual information. Now, it could. The arrangement of galaxies, the birth and death of stars, the evolution of structure all became recorded in radiation streaming endlessly outward. This is why astronomy works at all. The night sky is not a static picture, it is a layered history. Each point of light represents a different time, a different chapter, preserved because light was finally allowed to travel freely. This permanent transparency also meant that the universe could cool efficiently. Radiation escaped from dense regions, allowing gas to lose energy and collapse further. This enabled the formation of smaller, longer-lived stars. Stars like the Sun became possible only after light had reshaped the universe. Heavy elements, produced in the deaths of massive stars, further enhanced cooling. Carbon, oxygen, silicon, iron all radiate energy effectively. With them, gas clouds fragmented more easily, forming complex systems of stars and planets. Light and matter entered a partnership. As the universe aged, this partnership grew richer. Galaxies evolved. Star formation waxed and waned. Structures merged and reorganized. All of it happened under the watchful presence of light, recording every step. And yet, even as light became permanent, darkness did not disappear. Vast regions of space remain unlit, far from stars and galaxies. But this darkness is different. It is not silence, it is context. Darkness became the canvas, not the rule. As you lie still, letting your awareness soften, consider how light changed not just what the universe looked like, but how it behaved. It introduced complexity, feedback, memory, direction. Before stars, evolution was driven mostly by gravity and expansion. After stars, it became layered, dynamic, and interconnected. The universe grew more expressive. Light also made comparison possible. Bright against dim, near against far, past against present. Without light, differences blur. With light, structure becomes meaningful. This is why the arrival of permanent transparency marks the beginning of the universe we recognize. From this point onward, the cosmos became a place of stories, of events that left traces, of processes that could be observed long after they occurred. And yet, this transformation did not erase the past. The cosmic microwave background still glows faintly beneath it all, a reminder of an earlier transparency. The universe carries all its phases at once, layered, overlapping. Even now, as you rest in quiet darkness, ancient photons pass through you unnoticed. Light from the first stars continues its journey, diluted but intact. The universe is filled with messages, even when we are not listening. There is something deeply reassuring in that continuity. Nothing truly disappears. It changes form, it spreads out, it becomes quieter, but it remains. Light permanently changed the universe by allowing it to remember itself. And as that memory accumulated, the universe grew more intricate. Galaxies matured, planets formed, chemistry blossomed. Eventually, life emerged in small, protected corners. All of it depended on light being free. As we continue this calm journey through cosmic time, one final realization settles gently into place. The universe did not become meaningful when it became bright. It became meaningful when it could carry its own history forward. And as that history deepened, another question quietly waits ahead. What traces of the universe's silent era still remain, hidden within the cosmos we see today? Part 13. Why the universe remembers its silent era. Even today, the universe carries records of that darkness. The cosmic microwave background, the distribution of galaxies, and the large-scale structure of space all preserve traces of the silent era. Modern telescopes do not just look far away, they look back into this quiet past. The universe has no memory in the way living beings do. It does not recall, reflect, or narrate, and yet it remembers. Not through intention, but through persistence. Every phase it has passed through has left marks behind, etched into light, matter, and motion. The silent era, though long gone, remains present everywhere. The most direct memory of that time is the cosmic microwave background. This faint glow is not just old light. It is a photograph of the universe when it was less than 500,000 years old. Its tiny variations in temperature encode information about density, motion, and energy from an era when no stars existed. These variations are incredibly small, measured in millionths of a degree, and yet they are enough. From them, scientists reconstruct the universe's earliest structure. They reveal how matter was distributed, how fast space was expanding, and how gravity began its slow work. This means that the universe did not simply pass through the silent era and forget it. It carried it forward. As you rest now, breathing slowly, consider how subtle this memory is. Not loud, not dramatic, just a faint background hum, always present, always whispering. Beyond the cosmic microwave background, the universe remembers its silence through structure. The arrangement of galaxies across vast distances follows patterns laid down before stars existed. Filaments, voids, clusters, all trace back to tiny fluctuations seeded during the universe's earliest moments. When astronomers map the large-scale structure of the universe, they see this inheritance clearly. Galaxies are not scattered randomly. They follow a cosmic web shaped by gravity acting on primordial irregularities. This web is a fossil. Even the emptiest regions of space, the great cosmic voids, are part of this memory. They exist because matter flowed away from them toward denser regions long ago. Their emptiness is a consequence of early imbalance, preserved across billions of years. In this way, absence itself carries information. The universe also remembers through timing. The ages of stars, the evolution of galaxies, the chemical composition of matter, all point back to conditions set during the silent era. Hydrogen and helium dominate the cosmos because heavier elements did not exist then. Their later appearance tells a story of stars coming and going. Every atom heavier than helium is a reminder that there was once a time before it. Modern telescopes extend this memory even further. When we observe distant galaxies, we see them as they were long ago because light takes time to travel. Looking far into space is the same as looking back in time. Each deeper observation peels back another layer of cosmic history. The James Webb Space Telescope, for example, observes galaxies that formed only a few 100 million years after the Big Bang. Some of these galaxies appear surprisingly mature, already rotating, already structured. This tells us that the silent era did its work well. Structure was ready before light arrived in force. The universe did not stumble into complexity. It prepared for it. There is also memory hidden in motion. The way galaxies rotate, the way clusters move, the way matter flows along filaments, all reflect ancient conditions. Angular momentum acquired early persists. Motion, once established, continues unless disrupted. Even the spin of galaxies carries whispers of the universe's first asymmetries. On smaller scales, the distribution of elements remembers the first stars. Carbon and oxygen trace the deaths of early massive stars. Iron remembers supernovae. Gold remembers collisions between neutron stars. Each element is a timestamp, linking present matter to past events. Nothing is isolated from history. As you lie still, perhaps letting your thoughts drift, notice how this idea mirrors personal experience. Much of who we are is shaped long before we are aware of it. Early conditions leave lasting imprints. The universe is no different. The silent era mattered because it set boundaries. It determined how smooth the universe would be, how much structure could form, how fast complexity could emerge. Those constraints still shape reality today. If the early universe had been perfectly smooth, gravity would have had nothing to work with. No stars would have formed, no galaxies, no light beyond the background glow, a universe of eternal silence. If it had been too chaotic, structure would have collapsed too quickly, tearing itself apart. Balance was essential. The fact that the universe remembers its silent era tells us that this balance was achieved. Even cosmic expansion carries memory. The rate at which space stretches today depends on the energy content of the universe, much of which was set early on. Dark energy, dark matter, ordinary matter, all trace back to initial conditions. The universe's future is tied to its past. What is especially striking is how accessible this memory is. With the right instruments, with patience and care, we can read it. The universe does not hide its history completely. It encodes it gently in patterns and gradients and distributions. This is why cosmology is not speculation. It is archaeology. Scientists dig not into soil, but into light and structure, uncovering layers of time. And the deepest layer we can currently access is the silent era. Beyond it, opacity hides earlier moments from direct view. We infer them indirectly through theory and mathematical consistency. But the silent era stands as a boundary we can observe, measure, and study. That boundary shapes how we understand everything that came after. As you breathe in slowly, then out, it may bring comfort to know that nothing important is ever fully erased. Even silence leaves traces. Even darkness leaves patterns. The universe does not rush forward and abandon its past. It carries it along, woven into every new phase. In the glow of galaxies, the hum of background radiation, the arrangement of clusters, the universe continues to speak softly of its earliest quiet. And perhaps that is why this story resonates so deeply. Because it reminds us that stillness matters, that preparation matters, that long periods of quiet are not empty but formative. The silent era was not a gap between events, it was the foundation. As we approach the final parts of this journey, one thought settles gently into place. The universe is not just old, it is continuous, every moment connected, every phase remembered, even when it seems forgotten. And with that understanding, one final question waits quietly ahead. What does this long silence teach us about our place in a universe that took so long to learn how to shine? Part 14. What the silent universe teaches us about existence. The universe did not rush toward beauty or light, it waited. Complexity emerged slowly, guided by simple rules repeated endlessly. This long darkness reminds us that stillness is not absence, and silence is not emptiness. Creation does not always announce itself. For most of its history, the universe existed without spectacle. No stars pierced the darkness, no galaxies traced luminous arcs across space, and yet, everything that would one day matter was already taking shape. The laws were in place, the ingredients were present, time was doing its quiet work. This challenges how we often think about beginnings. We tend to imagine creation as sudden and dramatic. A spark, a burst, a moment that declares itself unmistakably. But the universe tells a different story. Its most important work happened slowly, invisibly, and without witnesses. In the silent era, nothing rushed. Expansion unfolded steadily. Gravity gathered patiently. Matter cooled gradually. There was no urgency because there was no deadline. The universe did not need to arrive anywhere. It only needed to continue. As you rest now, breathing gently, consider how unfamiliar this pace feels. Human lives are measured in urgency. We mark time with schedules, alarms, and expectations. We are taught to associate value with speed and visibility. But the universe assigns value differently. It values consistency. The same physical laws applied everywhere, every moment. No exceptions, no shortcuts. From this repetition, complexity emerged naturally. Not because the universe tried to make something beautiful, but because beauty is often a byproduct of stability sustained over time. The silent universe teaches us that absence of activity is often an illusion. What looks like nothing is often everything happening too slowly to notice. The early cosmos was full of motion, interaction, and change. It simply lacked contrast. This idea reaches beyond cosmology. In many parts of life, growth occurs beneath the surface. Foundations are laid quietly, skills develop unnoticed, understanding deepens without announcement. Only later does something visible emerge, and it feels sudden, even though it was years in the making. The universe is the ultimate example of this pattern. For hundreds of millions of years, it did not shine. And yet, during that time, it became capable of shining. It learned restraint, it learned balance, it learned how to let gravity work without interference. This patience was not a choice. It was a consequence of physical law, but it carries meaning nonetheless. In the silence, the universe refined itself. Another lesson lies in the simplicity of the rules that guided everything. Gravity pulls, energy spreads, space expands, matter responds. These principles are not complicated. They do not change. And yet, from them arose galaxies, stars, planets, chemistry, and life. Complexity did not require complex instructions. It required time. As you lie still, letting your thoughts soften, it may be comforting to remember that the universe itself did not begin complex. It grew into complexity, slowly, imperfectly, through countless small steps. This reminds us that imperfection is not failure. The early universe was not perfectly smooth, and that imperfection made everything possible. Tiny irregularities became galaxies, small differences became vast structures. Absolute uniformity would have meant eternal sameness. Difference allowed growth. The silent universe also teaches humility. It shows us that visibility is not the same as importance. The brightest objects in the cosmos, stars and quasars, exist for relatively short periods. The longest-lasting phases are often the quietest. Dark matter, which does not shine at all, dominates the mass of the universe. Dark energy, invisible and mysterious, governs its expansion. Light, though precious, is a minor component in the cosmic balance. This perspective gently reorders how we think about significance. We often assume that what is loud or visible must be central. The universe suggests otherwise. What shapes reality most profoundly often does so without spectacle. There is also a lesson in scale. The silent era lasted hundreds of millions of years. Human history spans only thousands, individual lives, decades. When we place our experiences within this larger context, urgency softens. Not because our lives do not matter, but because they are part of something far more patient. The universe did not hurry toward meaning. Meaning emerged because the universe allowed itself to unfold fully. It did not skip steps. It did not bypass stillness. As you breathe slowly, perhaps feeling the weight of the day easing, this idea can be grounding. You do not need to be constantly producing light to be real. You do not need to be visible to be becoming. The silent universe reminds us that existence itself is enough. Another quiet lesson comes from inevitability. Given the laws of physics and enough time, stars would form, galaxies would assemble, chemistry would grow rich. The universe did not have to be guided toward these outcomes. They followed naturally. This does not make existence trivial. It makes it resilient. Even in the absence of intention, complexity arose. Even in darkness, structure emerged. The universe did not require supervision to become what it is. That resilience echoes through everything that followed, through the formation of planets, through the emergence of life, through the long history of change that led to awareness. The silent era was not wasted time. It was essential. It also teaches us that beginnings are often misunderstood when viewed only from the end. Looking back, it is tempting to see the universe's early darkness as a prelude, a waiting room before the main event. But for the universe itself, there was no main event yet. There was only process. Meaning was not deferred. It was embedded. As you rest, letting your mind drift, consider how this reframes waiting in your own life. Waiting does not mean nothing is happening. It often means something is forming that cannot yet be seen. The universe waited until conditions were right, not out of caution, but out of necessity. When it acted completely. There is also comfort in knowing that the universe did not demand perfection. The first stars were unstable, Early galaxies were chaotic. Many structures formed and dissolved without leaving lasting traces. Progress did not require smoothness. It required persistence. The silent universe teaches us that creation is not a single act. It is a long conversation between law and time, between possibility and patience. And perhaps the deepest lesson is this: the universe existed long before it could be seen, and it will continue long after it can no longer be observed. Visibility is temporary. Existence is not. As you settle deeper into rest, this realization can feel calming. You are part of something that does not rush, that does not demand constant output, that allows space for stillness. The universe took its time learning how to shine, and when it finally did, it carried the memory of its silence forward. That silence is not gone. It still lives between the stars, in the vast spaces where light passes through without stopping, in the quiet background hum that fills all of space. The silent era was not erased, it was integrated. And as we move toward the final chapter of this journey, one last truth emerges gently from the darkness. The universe did not begin with light, and it did not need to, and neither do we. Part 15. Why darkness came first and light came later. Light feels fundamental to us, but the universe did not need it to exist. Matter formed, laws operated, and time flowed long before the first glow appeared. Darkness was not a failure of creation. It was a necessary stage, a calm foundation upon which everything visible was eventually built. It is natural to place light at the center of meaning. Our eyes depend on it. Our days are shaped by it. Our language equates light with knowledge, safety, and presence. But the universe does not share our priorities. For most of its history, it existed perfectly well without illumination. Darkness was not an accident, it was the default. In the earliest moments after the Big Bang, light existed but could not move. Later, it could move but had no sources. For long stretches of cosmic time, darkness was not something to overcome. It was simply the state of things. And within that state, everything essential was already happening. Matter assembled, gravity sculpted structure, time progressed relentlessly. None of these processes required light. This tells us something important. Light is not the engine of the universe. It is a byproduct. The laws that govern reality do not depend on illumination. Gravity pulls whether it is seen or not. Particles interact regardless of observation. Expansion stretches space without regard for visibility. The universe does not perform for an audience. As you rest now, breathing slowly, consider how unfamiliar this idea feels. We are so accustomed to measuring reality by what we can perceive, but the universe reminds us that perception is secondary. Existence comes first. Darkness allowed the universe to simplify. Without stars, without radiation feedback, gravity could work cleanly. Matter could settle into patterns dictated purely by initial conditions and physical law. There was no noise yet, no interference. This simplicity was crucial. If light had dominated too early, radiation pressure would have smoothed out differences. Structure might never have formed. Stars require imbalance. Galaxies require contrast. Darkness protected those delicate early variations until they could grow strong enough to survive illumination. In this sense, darkness was not absence, it was shelter. The universe needed time to organize itself before it could afford brightness. It needed gravity to establish frameworks before radiation could complicate them. It needed patience before expression. This order matters. Light introduces feedback. It heats gas. It disrupts collapse. It accelerates some processes while halting others. These effects are powerful, but they require structure to act upon. Without structure, light would erase as much as it created. Darkness came first because it allowed structure to form quietly. As you lie still, notice how often this pattern repeats. Foundations are laid in silence. Preparation happens out of view. Only later does something visible emerge, and when it does, it seems sudden even though it was long in the making. The universe is the largest example of this truth. Darkness also allowed the universe to conserve information. Early conditions were imprinted gently, without being overwritten by violent processes. Those imprints survive today in the cosmic microwave background and the large-scale structure of space. If the universe had lit up too soon, much of that information would have been lost, so darkness preserved memory. There is also something deeply stabilizing about the idea that the universe did not need to be seen to be real. It did not wait for observers. It did not delay its evolution until it could be admired. It simply existed, governed by rules, unfolding as it must. This challenges the notion that visibility equals importance. Many of the most influential components of the universe remain invisible even now. Dark matter shapes galaxies without emitting light. Dark energy drives expansion without revealing its nature. The brightest objects are often the least massive, the least enduring. Light draws attention, but it does not tell the whole story. As the universe aged and stars finally ignited, light transformed everything. But it did so on top of a foundation laid in darkness. Every star formed inside a gravitational structure that already existed. Every galaxy followed paths determined long before it shone. Light arrived late, but it arrived prepared. This sequence also reframes how we think about beginnings. The appearance of light feels like a beginning because it marks the point where things become visible to us. But visibility is not origin. It is revelation. The universe did not begin when it could be seen. It began when it could exist. And existence did not require light. As you breathe slowly, perhaps feeling the weight of this long journey settling gently, there is comfort. Here, darkness is not failure. It is not lack. It is often the condition that allows something deeper to form. The universe needed darkness to become what it is. It needed long stretches of quiet evolution. It needed time without interruption. It needed simplicity before complexity. It needed stillness before brilliance. Even today, darkness remains essential. Stars are born in dark clouds. Life develops in protected environments. Rest requires the absence of stimulation. Growth often begins away from light. The universe's earliest lesson repeats everywhere. Darkness came first because it was safe, because it was patient, because it allowed small differences to grow into lasting structures. Light came later because it could. When the universe was ready, when gravity had done its work, when matter had assembled into forms capable of sustaining fusion, light emerged naturally, not as a requirement, but as a consequence. And once it emerged, it changed everything. But it never erased the importance of what came before. As you settle deeper into rest, it may help to release the idea that progress must always be visible. That meaning must always shine. The universe itself does not support that belief. It tells a quieter story, a story where the most important chapters unfold without witnesses, where foundations matter more than displays, where patience is more powerful than urgency. The silent era was not a delay, it was the beginning, and light, when it finally arrived, did not replace the darkness, it rested upon it. Even now, between the stars, darkness dominates. Vast distances of space remain unlit. Light travels through them, but they do not produce it. The universe has not abandoned its original state. It has layered new possibilities on top of it. Darkness remains the canvas. As this long journey through the silent era comes to rest, one final understanding settles gently into place. The universe did not need light to exist, and it does not need constant brightness to be meaningful. It began in darkness, it grew in silence, and only later did it learn how to shine. As this quiet journey comes to a close, the universe gently returns to stillness. Before stars, before light, before anything could be seen. We've drifted through an era where existence did not announce itself, where time moved without clocks, where gravity shaped galaxies in darkness and light waited patiently for the right moment to appear. The silent universe reminds us that reality does not depend on being observed, and meaning does not require illumination. Even now, that silence has not vanished. It lingers between galaxies, beneath the glow of stars, and within the faint background hum that fills all of space. The universe carries its quiet beginnings forward, woven into everything that followed. And perhaps that is the most calming truth of all, that nothing rushed, that nothing was wasted, that even darkness had purpose. As you rest here, breathe breathing slowly. You are part of that same unfolding, held within a universe that learned patience before brilliance, one that took its time becoming what it is. Thank you for sharing this quiet moment with me. Your presence here, your willingness to listen, means more than words can easily express. If this journey brought you peace, may that calm stay with you as you drift into rest. The universe will keep turning. Time will keep flowing. And the silence will always be there when you need it. Sleep gently.